We're also going to consider pulleys in frames here in section 6.6. So if you recall what we did up here before, there's an external force and an external force, and this tension becomes an external force for our whole structure. And then we kind of glossed over what happens on the inside. So let's look at the internal forces here. If I take this pulley, separate it out, use the method of sections, and just draw a free body diagram of just the pulley. It's got the 75 that's going down. That's a tension there. The pulley has to transfer that force equal opposite, it just transfers the direction of the force, so we know that that is 75. If I just look at just the free body diagram of the pulley, and if I only consider those two forces, clearly it wouldn't be in equilibrium, but it does have an axle or a shaft or a point of support there. And that has to have the equal opposite forces like that. So there should be, because that's an axle, it should have a by and a bx. It acts like a pin. And so now we have a pulley that's in equilibrium. The shaft forces, axle forces, have to transfer equal opposite to this main body. And so if you see the by is going to get equal opposite, bx is going to be equal opposite. And so now I can draw a free body diagram of just the structure part of it without the pulleys. Doing the same thing with this pulley. Again, I don't know what this tension is. Those tensions are unknown, but the shaft transfers equal opposite. So here again, drawing a free body diagram of just the main structure, you can see what that looks like. And just another thing to note here is that because this force here is 75 as it goes around, it's attached to the frame here, which means that it has to be a 75 going that way. The same thing here, because this one over here is attached to the frame. Again, I don't know what that tension is, but it is attached to the frame going up. So those two external forces are still transferred to the frame, as well as the pin reactions from the pulleys, so that without 75 and that T, we now have a complete free body diagram of the main shaft structure. So the takeaway here is that pulleys have to transfer forces, or for pulleys to be in equilibrium, they have to have forces at the shaft. The shaft then has to transfer equal opposite to the main frame. So in this example problem, we have this weight hanging down. It's obviously putting a tension here. That tension is the same going that way. There's a two-force member here, and our desire is to find the reactions at A and at C. All right, so what can we do? We can separate the pulley, just like that. We know what this tension is because we know what the weight is. We know that forces have to transfer equal opposite so that they stay in equilibrium. These, I beg your pardon, you can determine the forces in the shaft by drawing them in there, and then you can do some of the forces in X and Y to discover them. But these forces have to transfer equal opposite to the end part of this member. The two-force member is in horizontal orientation. It looks like we've drawn it as a tension member pulling away from the joints of the tension of the two-force member. Therefore, it's pulling away where it attaches like that. We got a pin connection down here, and so therefore we have a free body diagram, or a set of free body diagrams here, which can help us analyze the thing. Now here's the option for you. You can take the pulley apart from the frame, or you can leave it attached. And in here I have a free body diagram of the pulley where it stays attached. In other words, we have a free body diagram of this part like that. We still have a tension over here, and we still have a tension going back. The reason this is equivalent is because the lever arms are increased just a little bit by the radius of the pulley, but it's increased on both sides. So, and indeed, if you did the sum of the forces of this versus this, you'd get the same. If you did moments of this versus this, you get the same answer. So these are equivalent descriptions, and so for your convenience, You may choose to take the pulley off of the shaft and draw it like this, or you may include the pulleys together. So let's walk through this problem 670. It's a similar kind of thing where there's a force being applied here. There's going to be some reactions here. There are no two force members here, but let's go ahead and draw the forces on the picture. So I'll say this is going to be AY, AX, BY, and BX. Okay, can I solve for any reactions before breaking it apart? Let's try. Sum of the moments about A equals 0. What have I got about A? Well, about A, I have BX and that. So let's go ahead and write those in there. So I got BX times 6 minus 50 times 8 is equal to 0. So BX is equal to 66.7. This is pounds. Then again, the structure together, sum of the forces in the x is equal to 0. Got minus bx plus ax plus 50 is equal to 0. So I have ax is equal to 16.7 pounds. All right, so I've got two components of the reaction, those two x components. I cannot solve for the y components, however. There's no way to break those, or no way to get those without breaking it apart. So let's break it apart. So for this example, I'm going to draw, I'm going to break it off, I'm going to take the pulley off of the standard there. So I'm going to say that this is 50 and this is 50, meaning this has got to be 50. And that one's going to be 50. It can't be anything different from that. And it didn't even give a letter here. So what did I call this? I think I'm going to call that point D. So I'll say that is dx, and that's equal to dy. Now let's draw a free body diagram of this portion, of this part right here, and see what we get. All right, so here I have all right, so here I have bx and by. I'm going to transfer dx and dy equal opposite. So I have 50. It's going up on there, which means it's going down on the pin here. And then I have 50 going this way. Then at the end here I have cy and cx. Okay, can I find out anything here? Well, let's try. I'm going to sum the moments about B. Okay, sum of the moments about B is equal to 0, so I got minus 50 times 4, minus 50 times 1.5. Those are these two. That times this lever arm, and that times this lever arm. Then I got plus cy times 8. That's equal to 0, so I can solve that for cy is equal to 34.38 pounds. All right, making some headway here. I can sum of the forces in the y direction. So what have I got? by plus cy minus 50 is equal to 0. So by is equal to 15.63. And can I find out anything else? How about some of the forces in the x? I think I can get there. All right, what have I got here? I've got minus bx plus 50 plus cx is equal to 0. And that gets me cx is equal to 16.67. All right, have I got all of the parts? I actually don't think I've solved for AY yet. So can I go back to the top, back to considering this whole thing and some of the forces in the Y? Let's go back up to here then and see what I can find. Sum of the forces in the y is equal to 0. So I got by plus ay. Is that all I have? By plus ay is equal to 0. Therefore, ay is equal to negative 15.63. Okay, so now I've solved for all of the pieces of the puzzle. I didn't actually even have to go here and try to solve anything there. I could have. That would have been an appropriate way of doing that. But let's just draw the free body diagram. I don't really have room here, but if you drew the free body diagram of that part, I'll do it right up here. I'm going to zoom out just a little bit. If you drew the free body diagram of that part of the shaft, you would have to include that 50 going up. And then the other parts have to be transferred equal opposites. So I'm going to say there's a CY and a CX. And then we can put AY and AX the way they were drawn originally. And you can do analysis on that free body diagram and you should get the same result. In fact, I think the textbook's solution does it that way. I think. I have to go back and look at that. But at any rate, make sure when you do this, you have to put that 50 in there because this is, and you have to put it in this correct spot. That spot right there has to be that spot right there for in terms of the lever arms. So if this is 4.5 feet and this is a half, so this distance here would be 3.5 feet. I should probably put that on here just so that you kind of have that for reference in case you run into a problem that's similar to that. Okay, this last problem is a similar problem in that you have a force pulling down here. There's going to be a tension here and a tension here. Again, you can model it two ways. You can either take these tensions and transfer them to this portion, that shaft or that pin here, or you can call this an external force and this an external force, like this. And again, then you have to keep it at the top of the radius of the pulley. And so you can either model it like this or like this. So for purposes of comparison, I modeled it like this. So I'm going to sum the moments about A here. And I have 1T with this lever arm and negative T times this lever arm, which are those T. Then I have this other tension right here, which is right there, which is T times 0.85, and that's going in the positive direction. So in other words, there are 3 T's associated with taking if you take the pulley off, you still have to include that tension that's attached there. I guess that's kind of the point. If you take the pulley off and transfer things to the pin, then you still have to consider that the tension here is part of the free body diagram. So when I did that, those are the 3 T's, then I still have the P going down, and I can find some relationship here. I guess we should probably look at the problem, but we're trying to find some sort of the largest force that can be acting so that the magnitude of the reaction at A does not exceed 2,000 newtons. Anyway, so here I have some relationships, some of the forces in the X, some of the forces in the Y. My limiting factor is that the magnitude of the resultant at A equals 2,000, which is going to be equal to the square root of the sum of the squares. I have solved for AY and AX in terms of T and P. So that's the square root of T squared plus P squared. And I know what the tensions were. I just plug those things in there, and I can solve this for P here as 742. So what I want to show you then is the textbook solution for doing it this way. And you can choose whether you think that this is easier or whether you think this is easier. This one is actually probably easier because you don't have so many attachment points. You don't have, you have to, by just keeping this as an external force, and then you don't have to include that internal force and you get the same answer. Now here's something quite curious. If you consider modeling it this way, let me zoom in here. Here's my free body diagram. Does it matter where this is attached? In other words, could you attach it here and get the same answer? Or here? Or here? In other words, it does not matter where you attach this force. In either way you do the problem, but it's easiest to see here that this is an internal force. This is an internal force, and it doesn't matter where you put it. It doesn't change the tension, regardless of what you do, regardless of where you attach it. So anyway, walk through that logic, if you would, and convince yourself that it doesn't matter where you attach it to still get the same tension here, because that's I'll try to design a homework problem and give one of those to you for your consideration.